They both deal with hypothesis tests. We just finished 10.1, which was an introduction to hypothesis tests and how to set up the hypothesis test. But I believe it's really important we do 10.3 first because that's with the means. And we just covered the means. So I think it's good to flow with that. Go right off, we just had to pull out a t-table and look at some t-scores. So we'll just stay with these means. These problems deal with some population mean. And I think it'll flow better. And then we'll cover 10.2. 10.2 is a hypothesis test for a population proportion. Okay? So we'll do 10.3 first. I think you'll like this. You'll notice it's not like this stuff. This stuff's kind of fun. This is the coolest part of the course. Because someone's making an educated guess. Someone out there is researchers. And we're going to see if the results are basically statistically significant. All that probability stuff we did. Like all that stuff we did with probability, now we get to apply it. Everything's based on chance. So we're looking at like, well maybe, I think this is what's going on in this world, or researcher believes that. Well, it's all based on chance. And do you remember what we considered basically rare in this course?
Less than 5.
Less than like 5%. Now it's not always the standard, we know that. Some things it might be less than 1%. You know, some may consider something less than 1%. They will give you that number in the book though. I'll talk about that. So, but when we get results where we're getting like, you know, a 1 in 1,000 chance, that's when we're going to challenge it. That's when we're going to have the evidence to go against it. Because we're going to say, boy, that's a very, very, very unlikely, you know, occurrence there that something happens. So that's what's going to provide us with the evidence. So this whole thing, it's kind of cool. Everything is based on probability, right? Everything's based on probability. And we all know when there's like a 25% chance of something happening, it could happen, right? That means like every 4 times it could happen. 25% chance. But when it's what? Really small, like 1 in a million, that's not happening, is it? Alright, so, hey, I'm going to start with the problem. The problem I'm going to do, it's like any problem in 10.3. I'm actually taking it from the previous edition of this textbook. Just because I figured everyone in this class would relate to it. I wanted to pick a problem to start with that everyone can relate with. We can all relate to the body temperature, right? Alright, so this was done in 1992, if you want to put down the year. And it was 3 scientists. And the first sentence is this. We're going to set up a hypothesis test and perform a hypothesis test. The first sentence is, the mean body temperatures of human beings is assumed to be 98.6 degrees Fahrenheit. So the first thing we're going to do is set up our hypothesis test, okay? So I'm going to get ready to start setting this hypothesis test up. So I can go here and I'll put, so this is the setup of the hypothesis test. This is the null hypothesis. This is the alternative hypothesis. I'll read that first statement again. The mean body temperatures of human beings is assumed to be 98.6 degrees Fahrenheit. They like to state the status quo in the first sentence. So, when I begin, which symbol do you think I'm using?
The left one.
Yeah, it's this one. Now you might go, well, if we're doing means, that's how I knew it. But did you hear a percentage? 98.6 degrees Fahrenheit. Now that's like a mean, so we're going to use mean. So I'll put mu, I'll put equals, 98.6. Good job, this is what we're doing. Hey, that'll be section 10.2. We'll do the row, which is the population proportion. Okay. Now what about this? This depends on what these researchers believe. It's their educated guess from all their experiences. The next sentence, it says the 3 researchers believe that the body temperature is less than that number. So what symbol will I put?
Less than.
So down here, when I'll use the same parameter, mu, the same number, 98.6, and then because they said less than, just like that. Cool? Any questions on this so far? And I do have to emphasize how important that is. Because that symbol right there is actually going to dictate our entire performance of the hypothesis test. So we've got to make sure we get it right. But I know you can read the sentence. We know greater than means what? That way, less than means that way. So eventually you and I are going to be making a bell, drawing a bell, and we're going to shade one tail. So this is very important, that symbol. All right, now, here come some numbers. So every time a number, I think it's good to write it off to the side. So the first number is this. This is from his old text. All right, they recorded 700 measurements of body temperatures. And these were randomly selected humans. They did it for 3 days, if anybody wanted to know that, but we don't need the 3 days. So let's go down. They recorded everyone's 700 body temperatures of humans over a 3-day period. So what is equal to the 700?
N.
All right, so I'm going to go up to the side on just to list this. We got, all right, well, you know, when you read these word problems, they're long. We just want to record the important stuff. So n equals 700. Hey, this is for means, isn't it?
Mm-hmm.
So with means, everyone, we are going to use what's called a t-table. Remember with inferential statistics dealing with means, we always use the t-table. So I'm going to write this down right now. If n is 700, what would the degrees of freedom be?
699.
Yeah, we just subtract it by 1. And don't worry if you didn't know that. It takes a while sometimes. df is always equal to sample size minus 1. Degrees of freedom minus 1. All right, what's next? What else did they get from these 700 humans? The sample mean was 98.2 degrees Fahrenheit. They said the sample mean is 98.2 degrees Fahrenheit. Sample mean means x bar, right? Now, if you need to, write the word sample mean next to that, just so you know what that means. But I know everyone in here knows that's the sample mean. All right, 98.2 degrees Fahrenheit. That's your sample mean. All right, standard deviation of the sample, 0.7. What's the symbol for standard deviation?
S.
S equals 0.7. Cool?
Can you use S of X bar in the way in the calculator they do it?
Yeah, that's a good point. All right, everyone. Just to let everyone know, the calculator puts a subscript S right there off that S. So just so you know that, the TID 384 does put an X on the subscript on that. Textbook just puts a what? An S when they're talking about the sample standard deviation. Well, feel free to put a subscript of X there. Okay. Everyone so far so good? There is a new number coming. We haven't talked about this yet, but I'll make sure to explain it to you. They give something called the level of significance. And for this particular problem, everyone, they said the level of significance is 0.01. Now I'm going to change colors of chalk. So I did everything in white chalk so far, right? And if you want to be like me, you got a pen and a pencil, feel free to do the same thing. You don't have to do it today, but every time I do a hypothesis test, I'll do this. For the level of significance, I'm going to change colors and just write this number down. The level of significance, we'll explain what it means, is 0.01. Now look at the Greek letter they used for the level of significance. They used the Greek letter alpha. So we haven't seen that Greek letter yet. They like to use alpha. That's alpha, the Greek letter alpha for the level of significance. But I like to change chalk and keep it separate from all these numbers, which I did in the white chalk. You'll see why. When I draw our picture, we make our bell curve, I think it's important. Just to distinguish the difference between this and this. Alright, so everyone, the first thing was, we set up the hypothesis test. I'm just going to put a line here. You can check this off. The setup of the hypothesis test is complete. Alright, well, what do you do next? Well, someone did a study, they got their results here. Before we go and perform the hypothesis test, we do have to verify our requirements. So let's put that down. We're going to verify any requirements to ensure that the distribution of the sample mean is approximately normal. Cool? That's what we're going to do. Verify our requirements to ensure that the distribution of sample mean is approximately normal. What is it for means? Do you remember?
N greater than 30.
N greater than equal to 30. Everyone, is the sample size greater than equal to 30?
Yes.
Well over 30, right everyone? And we're fine. We're fine. Hey, also, do you remember I said it? They chose these people randomly? That's important. I'm going to write that down. It's a random sample. And when it was a random sample, So we have verified requirements. All right, we are now going to perform the hypothesis test. All right. So we're going to start with what's called the classical approach. Right now, everyone, we are now going to perform the hypothesis test. And there's two approaches. We'll do both of them, because they both go hand in hand. One's called the classical approach, one's called the p-value approach. So we're going to perform the classical approach. With the classical approach, everyone, now that we know that the distribution of the sample mean is approximately normal, you and I are going to draw a bell. We're going to draw a bell curve. Now, before I forget, because I don't want us to get confused, am I using Z or am I going to use T?
T.
Because there's like a Z distribution and there's a T distribution. And with means, mean Mr. T, we always use what? So just as a reminder, I'll put a T in here. Just in the middle. Just let it stand out so I don't accidentally use Z with these problems. And then in the end, we can all discuss how troublesome it would have been if I accidentally did use Z. Because everyone, keep in mind, the T distribution was for very small sample sizes, right? Mm-hmm. That's a gigantic what? Sample size. I might as well whisper this to you. In this particular problem, it really wouldn't matter if we use Z, because that number's huge, isn't it? Isn't that close to 1,000? Mm-hmm. I mean, it really is. So that sample size that big, it wouldn't make a big difference if we accidentally use Z. But it's good to stay what? Always consistent. Hey, we're doing inferential stats with means, we're going to use T. So we're going to use the T distribution. And what's T equal to in the middle? 0. What's T equal to like right there? 1. They're like z-scores. T equals 2. 3 standard deviations from the mean. What's T equal to here?
3.
T's negative on each side, right? Mm-hmm. If you want to label this. Sure. All right. So we're performing a classical approach. We've got our bell curve drawn. I am changing colors. All right, so when I have my yellow chalk out, I'm going to that level of significance. What I'm going to do is shade a portion of that bell curve. I'm only shading 1%, and I'm going to shade one of the tails. Guess which tail I'm going to shade? It's all based off that. Yes, very good. Gary, excellent. I'm shading the left tail. This is called a left tail test. Because of that symbol right there, this is telling me which tail to shade. I'm going to shade over here, but I'm only shading what? Not much. I'm only shading
1%.
Yeah, 1%. So not much. If you want, everyone, you can put a an arrow, because this would shade what? Forever. Does that make sense? I mean, I'll move my verification of the requirements just out of the way so everyone can see this. That you're like, yeah, this bell curve, it really just goes on forever. And I'm saying the shaded region 1%, there's not much left over, but I'm going on forever that way. Shaded region. All right. You know when we did verify the requirements? Where n was greater than equal to 30, and the sample was, I'll write SRS for it was a simple random sample. I'll keep that there. I just wanted you to see that this bell really keeps going forever, doesn't it? I shade 1%, but you can think of everything to the left shaded. All right. But when I put that in yellow chalk, this is the alpha level, which was equal to 1%, right? Mm-hmm. All right. There's two numbers we got to find in the classical approach. This isn't bad at all. We got to find something called a, well, it's not T. I mean, it's not Z, it's T. We got to find something called a T crit. It's the critical T value. So off this wall of that shaded region, I'm just going to extend this line down here, and this marking right here, you and I have to find this critical T value. But feel free to just call it T sub crit. You know, but if you want to write it in words, you could say it's the critical T value. We have to find it. You go, well, how are we going to do that? Now I'm going to notice I'm with the yellow chalk, because we're going to get the critical T value. And it's based off this number here and it's based off the degrees of freedom. All right? But that's what I mean. Sometimes students get confused, like, I don't know how to get the critical T value. That's why I like the color code. How am I going to find this critical T? I got my yellow chalk. It's based off this what? 0.01. So does everyone have their T tables?
Mm-hmm.
We're going to look at this T distribution. Look in the left column, excuse me, the top row for a 0.01. I want to see the 0.01 in the top row. So we go up to the top row, we're looking for 0.01. Then we're going to look over to DF, which is degrees of freedom, and we're going to line up the degrees of freedom, that's 700, with the 0.01 to come up with this critical T value. Now, is there a 700 in the left column?
No.
So we take the closest. What's the closest degrees of freedom you see to 700? Yeah, what's closer to 700, 100 or 1,000?
1,000.
We're going to use the 1,000. Cool? Gary, okay?
I thought the degrees of freedom was 699.
You're right. Oh, so degrees of freedom, thank you, Gary, is 699, and I'm going to take the closest number to 699. Now, there's 1,000 and 100. And Gary, thanks again. We're taking the closest number to this 699. So I'll write that down, get 699 degrees of freedom. But the closest to this, everyone in that table, is the what? Is the 1,000. Well, it's fine. That's what we're going to use. So what do you all get when you line up 1,000 with 0.01? 2.33. What's after the 3?
0.
Now, everyone, look at my sketch. See, there's a reason. We just want to give you one nice table, right? There's something else I have to do. This isn't making sense. This is why I like to label these. T equals 0, T equals 1, T equals 2, T equals 3, negative 1, negative 2, negative 3. Doesn't a T-score on the left side have to be negative?
Mm-hmm.
So make sure when you're drawing your pictures and using this T-table, if you ever find a value that's on the left side, just put a negative in front of it. And I think that's okay for everyone. I've never had any students have trouble with that because that would mean we're not going to give you a whole nother sheet for you to copy, right? Yeah, we just need one sheet. We know about symmetry, true? So our critical T value is negative 2.330. Cool? Hey, if anybody's curious and they wanted to get this off their calculator, who does have the nifty new calculators? I will point this out. You would have had to type in inverse T, 0.01, comma, 699 like Gary indicates. And the newer calculators do this. But who's got an 83 like me? Doesn't work on ours. Right? Angela, do you have that?
I have it, yeah.
So, Edwin, would you hit this? You can tell the class what comes up. She's going to hit this on a calculator. It's going to be, we noticed, just a little off, like the number we saw last class. Let's see what she gets.
Negative 2.331694.
So it had a 1 right there.
Yeah.
With the technology. More accurate, but this is good enough, isn't it? Absolutely. We're good to go. So very good, Angela. Feel free to use that negative 2.331. All right, so we found that. That's the inverse T function. I don't have that, so I'll erase that. But that's where we can get it off the new models. There's one other number we got to get to perform this classical approach. It's what we're going to compare to this. It's called the sample test statistic. All right. They label that as T naught, or T sub 0. But I think we should put words next to this so we know what this means. This is called the sample test statistic. All right. Now I want you to notice something. I changed colors of chalk. I think it's good to color code. I only needed this yellow chalk. Look, I'm putting it down. I don't need it anymore. I only needed that yellow chalk from the 0.01 to get my what? My T crit. That's all I needed it for. Does that make sense? See, the rest of the way I'm using this white chalk. Now I'm back to, oh, sample. Now I'm based on my sample results, okay? Just so we're not confused with all these numbers. This critical T value comes from the level significance. And if you're curious, like, what is that level significance? Those three researchers considered anything less than 1% to be rare or unusual. Bless you. So when they began the problem, that's what they were thinking. Anything less than 1%, we're going to consider as unusual. All right? Now, we're going to get this. All right? Now, how do you get this? Well, this is like when we did z-scores. Do you remember the z-score like this? x minus mu, and we went like this, remember this?
Mm-hmm.
And then if it dealt with sample means, this is what we had to do. We had to do x bar minus mu, and you had to divide this is what we did in 8.1. But then we realized something in chapter 9 when we realized, oh, there was some bias involved, and so with the means, when we do inferential stats, we use t rather than z. So that looks like this, but here it is. The formula is x bar minus mu all over the sample standard deviation by divided square root of it. And we'll do all these calculations. Hey, just so you're not freaking out, this formula sheet, do you see that on there? Go ahead and look. Look in chapter 10 portion of the formulas. And look where I wrote examples. Does everyone see my examples? Take a second to look at it. So you're just like, man, I forget that. The sample test statistic, T naught, is going to be a number based off our sample. Does everyone see it on there? Yeah? All right, good. So you know it's there, right? In case you forgot that, it's there, true? It's on this one. It's on. Do you have that copy of the test? The thing that gets attached to us? You see it right here in section 10 where it says examples. And I got T naught equal to x bar minus the mu. I actually put a mu naught here, but that mu, everyone, is that number right there. That's that status quo. All right, so you and I are going to do all this math. Then we're going to compare this number to this number. Cool? And then we'll have our conclusion. Yeah, we'll almost be done. All right. Let's fill in the blanks. What's x bar?
98.2.
All right, 98.2. Minus, what was the mu for this problem? That's the status quo.
98.6.
Good job. Hey, that's coming out negative. Yeah, it should be. It's, everything's on the left side, right? Okay. What's us? 0.7 and the square root of... All right, Gary, this time I'll use the 700 because it's in that, right? All right. Now be careful typing this in. And you want to do it all at once, you can, but you got to be careful with the what? The parentheses. So when I'm going to type this all at once on my calculator, but if you like to do it in steps, that's not a bad idea. I'll do it both ways, just so you're fine. It's an important number, so I got to make sure I don't mess it up, right? So come out here. Let's see what we get here. All right. So parentheses, 98.2 minus 98.6 close parentheses. So when I put parentheses around that, now I hit division, and when I do this division, does everyone see when I wrote this on the board, I put parentheses here? If I try to type this all out at once, I got to be very careful with these parentheses. Divided by parentheses, 0.7 divided by square root of 700, close that parentheses, close that parentheses. And this will be fine. Should be a negative answer, as we know. And that could be the craziest z-score or t-score we've seen in this class yet. But I'm going to write that down, okay? But I did it all at once. If that's too much for you, there's nothing wrong with doing these in 2 steps, okay? And I'm just going to put negative 15.1. Okay? Hey, some students do 2 things at once. They go like this. What's 98.2 minus 98.6? They hit enter. They do the other thing. What's 0.7 divided by the square root of 700? And they hit enter. And then they go, what's negative 0.4 divided by my answer? And when you know where the answer button is, right? Some students prefer to do this because they're worried they're going to mess up all the what? All the parentheses. So it's not a bad idea. And I still get the same number. Cool. Hey, I'm going to hit the lights. Everyone, come on now. Isn't that the most ridiculous or outrageous z-score, t-score we've seen so far? That's way out there. What kind of z-scores do we usually get? 1s and 2s and 3s and negative 1s. Everything in here, right? Where is this thing in this image?
All the way over there.
Oh my gosh. I mean, it's way over here. So this is going to give us an idea of what's going to go on with our conclusion and what we feel about this whole experiment and what we could say about our hypothesis test. But everyone, I think it's important that we all put this in our image. All right? I want us to make a marking. We know where the t crit is, right? go plot this, like actually in your picture. Well, okay, if I plotted my picture, how far over am I going? Oh my gosh, so I'm like way over here, right? And this number is way, way over here. I don't even think I exaggerated enough. It's probably even further, right?
Mm-hmm.
But it's way over here. The key is T naught equal to negative 15.11. And it's called the sample test statistic. That's what it's called. Evan, can you make this observation for me? Is it in the yellow region? That yellow region that dealt with this level significance.
Mm-hmm.
So what I'm doing now is, remember how we said this bell curve continues forever? Well, doesn't this yellow shaded region go on forever?
Mm-hmm.
This is called the critical region. If you're wondering, this yellow region, it's called the critical region. That's the T crit value. But what's so important that we have to do at the very, very end of performing the classical approach is to determine whether or not our sample tested statistic fell in the critical region. Does it? That's what we got to look at. We got to make that observation. So the picture is actually important. It's important to make this picture. Everyone, is our sample test statistic falling inside some portion of the critical region?
Yes, it does.
All right, so bless you. Put this in your notes. This is what we do with hypothesis tests. So I'll start with it. If your sample test statistic falls inside the critical region, we are going to reject the null. I'll say that a couple times. That's what we're going to do for every hypothesis test. Every hypothesis test, once we get, we're going to compare two numbers, right? There's going to be a t-crit and a sample test statistic. If our sample test statistic falls inside the critical region, you go, what are we going to do? We are going to reject that null hypothesis. Now, I'm sure you're wondering why. Don't worry, I'll explain why before you leave today. Because you might be going, okay, but why? I get it. I get it, Professor, but why? And we'll get to that. I want to explain why. It's all based on probability. This whole thing was based on actual probability. Right? What's the probability it's going to, like, rain today? Or what's the probability somebody dies next year? And all that stuff we talked about in this course. But I'm going to say one more time, oh, you bet. If your sample test statistic, it's that T naught thing, if it falls inside the critical region, which you already have drawn, we reject the hoe. You know what I mean by the hoe, right? Yeah, you should get it. The null hypothesis. You can write that. The H naught, we reject it. So guess what, everyone? What if it doesn't fall inside the critical region? What if it falls like here?
We accept it.
Then we do, yep. And we can't say accept because it's like the courtroom, you're saying someone's innocent, right? So we'll say we do not reject it. Right? Just like in law, we never go, we find him innocent, Your Honor. We just go, we find him not guilty. We just say we do not reject. Not guilty, we do not reject. We would say that if it fell somewhere over here. But we're going to be rejecting the null in this thing. Do you agree?
Mm-hmm.
I mean, if you want to go off to the side, we already know with this problem, what are we doing? Reject what?
Null hypothesis.
Reject the hoe. That's what we're doing with this problem, aren't we? Reject it. Reject the H naught. All right, we're rejecting it. Now, when we're ready to write the conclusion, we can make a concluding statement right now. All right, so we're rejecting the hoe, right? I will write that again, so I'll erase it. I'll show you where I like that. But we all know we're rejecting this thing. We're basically saying what? Reject you, go with this, right? We're like, check mark, you're out. This is what's going on here. Do you follow me? Mm-hmm. And someone spent a lot of time and money on this, but it looks like their educated guess was pretty much going with what they thought. All right? Cool. Here's our conclusion. So you and I are going to state the conclusion. State the conclusion. State the conclusion to your hypothesis. And when we say the same thing every time, it's kind of cool. We either say there is evidence, or we say there is not evidence. right? And when in this case, there is evidence. You might say there's strong evidence. There is evidence suggesting that, I'll wait till I write that. There is evidence suggesting that, we use words like suggesting in stats. We're never 100% accurate, right? We estimate. There is evidence suggesting that, and I'm just going to write this. I'm just going to write this right here. You always state the alternative hypothesis. That mu is less than 98.6. You don't write the 98.2. You don't write the 98.2. If you want to use words, you could say the population mean is less than, if you want to put words in there, but it's okay to write it like that. So let me emphasize this. When you state your conclusion, you always refer to this. Somehow in your conclusion. You will always say this somewhere. Why? Because that's what you were putting all the time into. That's what these researchers were trying to look at. They were trying to look at this. So you got to state it in your conclusion, right? Well, there either is evidence or there is not evidence. When this falls in a critical region, there is evidence. Okay? Hey, just so everyone has this. What if the sample test statistic came out over here? Then we would have said the same statement, exactly word for word, but right here I would have put the word not. And I would have said, there is not evidence. Right?
Not or no evidence.
Yep. You can say that. That's good. He goes, there's no evidence. You can say there's not evidence, but even better, I like the there is no evidence, suggesting that. What's most important, or what we can't say is, we're keeping the null. We can't say that, because that's just like in law saying, oh, we find him innocent, Your Honor. We just say there's no evidence.
But
right?
who came up with this nomenclature? Like, is there like?
Oh yeah, it's this stuff based off just like with you see in terms of law and how people are arguing versus we find them guilty or not guilty. It's the same thing. We're saying either we're going to what? Reject or not reject?
No,
I know. Because we got to assume like if we said keep that, there might if we didn't have the evidence, maybe we screwed up something, right?
Huh.
Maybe we messed something up in our studies. Not a numerical error, but maybe there was what? Some kind of bias involved. Or some kind of lurking variable, or some kind of confounding factor.
Yeah.
So because of all these other factors that we're not aware of, we just say, all right, there is evidence or there's not evidence. We reject this or we do not reject it. Hey, everyone good with this? Awesome, Sierra.
So if, so like you were saying about if the sample test statistics falls outside of the critical region, then we fail to reject the null hypothesis.
That's true.
And then in the conclusion, it would be there's no evidence suggesting that mu is less than 98.6. Okay.
You nailed it. And when Sierra that was perfect. She was saying if that sample test statistic, which was negative 15, came out over here like negative 1.3. She started out saying there is no evidence suggesting that mu is less than that. That's what she'd say. And she also mentioned that you would fail to reject this. That's what she said. She goes, you would fail to reject this. We just can't say you would keep it. You can whisper it to yourself though, right? I think the best word art you can say is retain. You can be like, oh, we're retaining it. We'll retain it. It keeps such a strong word, it sounds like, oh, it's right. We're like, well, we just didn't have evidence to go against it. That's all.
Are you going to ask us to state both in the test, like what Sarah just said?
Oh, no, this is fine. This is, when it comes to conclusion, you can just every time go, there is evidence or there is no evidence suggesting, and you always report what? The alternative hypothesis in your conclusion statement. Now we're going to do, Holland, we're going to do another test. I left some room over here, everyone. There's another test we're going to do. It complements this. And it gives us the understanding of why we're doing this. Like, great, Professor, you told me I'm going to reject it with this. Sarah, and you said it perfectly, but it's like, why? Why is this the case? Everything was based on probability. So this next test, it's a probability test, and it's called the p-value test. Oh, go ahead, Michael.
How did you get the sample mean again?
The sample mean was given to us from the textbook, from the former version. That's where I grabbed this problem. But those 3 researchers went out and got body temperatures over a 3-day period. And of all those body temperatures, that was the mean of those actual humans. Now, it was done over 20 years ago. But it really was done. It was reported, it was published and everything. Cool. Any nurses in here? Know about this? Rick, you get this? The Journal of, it's American Medicine Association or something like that. All right. Everyone, but it was published back in '92. We are now going to put up a little wall here. Everyone, we are going to perform the p-value approach. All right. Yes, we'll do both. This complements this. Even though we already know the solution. Isn't that funny, Sierra? We already know the answer. We know the answer. This is going to complement this because the p-value is important to us.
So you're only going to have us do one of these on the test or both?
Yeah, you'll do both. You'll do both of these. It's not bad though, Gary, because we'll use the technology to facilitate this. We'll be all right.
Oh.
No. Wait, so you were doing it the long way first? Again?
He always
Let me finish this, and then I'll get You'll be all right. It's not bad. Hey, we're now going to perform the p-value approach. And when the p-value is a probability. So that's the first thing. We got to know what the p-value is. The p-value is a probability. Well, the p-value is a probability. We want to know why we're doing this. Why were we rejecting a null here? This being in the critical region. So we're going to perform what's called the p-value approach. So we start out by finding the p-value. And the p-value, everyone, is a probability. I'll show you, we're going to write the number right here. The p-value is the probability that, and when I'm looking for my x-bar, where is it?
98.2.
Right there. And this was on the left side, left tail test. This is the probability that x-bar was less than or equal to 98.2. And I'm going to write this again. Didn't we already find a t-value associated with that?
Mm-hmm.
Yeah.
So I'm now going to put what was the t-value associated with our 98.2? I'm going to write it underneath.
Negative 15.1.
Some of you might have a sense of this probability in your head, but we'll use the calculator to get this. Okay? What I'm basically saying here is from this marking over to that side, what portion, what area of this bell curve is shaded? It's not much, is it? Not much is shaded over there. This is going to be a very, very, very low number. Because as you're thinking about this right now, you got to be thinking, how much to the left of negative 15 standard deviations is shaded under that bell curve? Oh my gosh, it's not much, is it?
Yeah.
So I want to expect a very, 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 very what?
Small number.
Small number. Do you all agree? We'll do it on the calculator, but we know right now, just looking at this bell curve, we know about the empirical rule and everything. My gosh, this is going to be very, very, very small. Do you agree? All right. Very, very small. So how do I do this on a calculator? Do you remember we always used normal CDF on the last test?
Mm-hmm.
Well, that dealt with z-scores. That dealt with z-scores. We're now doing what? T-scores? So we're going to use something called TCDF. Cool? We'll use TCDF. Now, does everyone remember the things we always had to do? Was it 1E99 or negative 1E99?
Negative 199.
We use negative 1E99 for negative infinity. What's this t-value here?
15.1. Negative 15.1.
15.1. And then
0 and 1.
we'll just put the degrees of freedom. Will that work?
Okay.
What's the degrees of freedom for this?
699.
Let's try. Every calculator has a TCDF button. Well, right now, take a moment before I pop it up here. Would you look under distribution? See if you see TCDF.
Number 5.
Okay. All right. Now, don't we all agree we're expecting a very small number? I mean, so small, probably close to what? Think about this. How far from here to the left is shaded? Not much, right? Isn't 99% in here? 99%'s in here. There's not going to be much here. So expect something puny, really small, like these small probabilities we get. So let's go to here. Secondist. To get that, I hit second bars. TCDF. Not normal CDF, but what? TCDF. All right, what's the lowest number? Negative 1E99. Whoops. Let me delete that. Negative 1E99, comma. Negative 15.1, comma. What's the degrees of freedom?
699.
We're expecting something very small. I wonder what the calculator's going to say. It was so small, the calculator went to what? 0, which makes sense to us. And when we're saying the probability is what? What chance?
0.
All right, so I'm going to put 0%. You can put a squiggle if you want to say it's about 0% chance. Because the p-value is a probability. And before you get so concerned, when you're like, man, that's going to be hard to remember all this, you watch. You know how we wrap up these classes? We go, isn't there a cool button that could do like 90% of this? And we're like, yeah. And Gary, we're going to love that. So don't worry about that. But what's important to us is, this number is so important to me as your instructor. I want to make sure everyone understands this. This is a probability, right? This is what this whole hypothesis test was based on. It was based on chance. And what we're saying is this. That when everyone in the world was saying the body temperature was what? 98.6. These three researchers disagreed. They probably took body temperatures and thought it was a little what? Lower, like, you know, something around 98.4, 98.3. So they went out and took all these measurements. What did they get for the sample mean? 98.2. Now that is lower. We all can see that. Do you all agree it's lower? What we're looking at in this course is, we know it's lower. We want to know if it's statistically significant. All right, so I'm going to repeat that. You can put that in your notes. It's really important. This is what we're looking at. That's lower. Yeah, we get that. We want to know that this number being lower than this, is it statistically significant? You know, do we have evidence to show that this is statistically significant? The only way we can come up with that is through this probability value, which is a p-value. This is going to tell us. And you go, what are we looking at? Well, what do we consider rare in this world? What have we used in the textbook?
Less than 5.
Less than 5%. But these three researchers said, what's going to be rare? Anything less than what? 1%. So, and here's how it goes. If your p-value that you get, if it's lower than the alpha level, then you're going to reject the hell. Let me say it again. If your p-value is lower than the alpha level, you know, we're going to reject that null hypothesis. Now, you want to know why? Here's what's going on. If we're getting a probability that there's a 0% chance of getting this, but didn't the researchers get this? Let me say that again. The chances of getting this sample right here, the odds of getting it, is the same chances of me dying today and having my house burned down and having 2 heart attacks and a stroke in the same day. Now, is that going to happen?
No.
But this really did happen. So we're like, then something must be wrong then. What's wrong? We're saying that's wrong. Does that make sense?
0% chance that
There's a 0% chance that someone could go out and get these results right here, approximately 0, if this is really the real deal. It's with an if statement. If this is really the real deal. So we go, oh, well, you're getting 0%. Nothing in this world happens with that 0% chance. So what's going on? You must be messed up. Because we really did get this. We're saying the chances of getting this, with that being the population mean, is basically what? 0%. So there's our argument. Isn't that cool? And they use this stuff in law. They do. They'll use this stuff in the courtroom. Garrett?
The level of significance is always given, correct?
Absolutely. Great question. Great question. He says this will all be given. If Gary went out and did his own study, and if he did it with a team of people, you're going to determine before you start your level of significance. You might use 0.05. Most problems use 5%. I guess these three were really serious, huh? They were like, hey, it's got to be less than 1%. But boy, that's less than 1%. Does everyone agree? So great job. Hey, we are now going to interpret this because this gives us meaning to this whole problem. Okay? So here it comes. Well, oops. I'm going to interpret the p-value. All right. Why are we doing this? This gives us meaning to this whole problem. We now know why we're rejecting the null hypothesis. It was based on probability, right? All right. Interpret this p-value. This is the probability. See, that's the first thing. We know it's a probability, right? If you don't like the word probability, you can say chance. This is the probability of obtaining these statistical results. Wow. These statistical results. This is the probability of obtaining these statistical results. And by me saying these, I'm talking about right here. So if you want me to just draw a little arrow here, what do I mean by these? This stuff. That right there. This is the probability of obtaining these statistical results. And then I'm going to put this really big. If! If mu is really, truly 98.6 degrees Fahrenheit. That was the status quo, right? And I'll put a period. I'll put one more sentence. Well, this is my first sentence. This is the probability of obtaining these results here, of getting them, going out in the world and getting them, if mu is really what? 98.6. Now I'm going to put the word because. Where I went, because the p-value is lower than the alpha level. So I get to change chalk. And what's the alpha level? The level of significance. What was it?
0.01.
So I'm gonna, because the p-value is lower than this guy, this was 0.01, but wasn't this lower? This was what? 0. 0.00. Because the p-value is lower than this is where I like to make this final statement. We reject H naught. We reject the null hypothesis. Or if you want to say it, we reject ho. And when I know it sounds funny, you know why I say ho sometimes? It helps students remember this. Here's a phrase, I'm telling you. Because you can get confused, you get a test, you go, oh my gosh, I'm confusing this. I'm getting confused on a test. Well, how about this phrase? If your p-value is low, reject the ho. I mean, it may be something that'll just help you remember this, right? If your p-value is low, what are we going to do?
Reject the ho.
Reject the ho. And then just remember, if my p-value is low, I'm going to reject it. And you go, well, how low? Lower than the alpha level. So when you go, well, how low? Lower than the level of significance, the alpha level. I know, and I'll say it next class too, so people always remember this. If my p-value is low, I'm going to reject the ho, right? We're rejecting you, we're saying you're out, we're going check mark, we have evidence for this, right? Actually, we have strong evidence, right? Oh, and let me say this again. I didn't write this down, but you can if you want, Sierra. You could really write this. This means our results are statistically significant. That's something, I'm sure you've heard that before, probably in your other classes. You've probably read about this in literature, or in just some of your, your readings. Maybe it's in a biology class, science class, etc. But our results are statistically significant. We all can see that this is lower than that, right? We wanted to see by that being lower whether the results statistically significant, and they are. Now, you know what's interesting to me when this whole study was done? It really was done. But to this day, guess what everyone tells me? I go, what's the mean body temperature? Everyone still says what? 98.6. I mean, sometimes numbers just what? Stick around. Here's a second thing I'm curious about. This problem used to be in his textbook. He took it out. So now I'm wondering why. I got to get an answer. If he came to visit here a couple years ago, the author, next time I see him, I'll ask him. I want to know, like, was there evidence of what? Maybe there was some confounding factor in that study. Maybe it wasn't random enough. Maybe they took all the body temperatures and it was freezing cold in the room, right? You know what I mean? Something that confounded the situation, and someone said, nah, that study was bogus. And so they threw it out. So I'm curious. Or if he just got tired of having it in his textbook, right? But it really was done. It's kind of neat. I mean, because that's strong evidence, isn't it? But to this day, we still say what? Oh, the average body temperature is what? 98.6. So I guess a good lesson to get out of this, don't get too stressed if you have a son or daughter and their body temperature is 98.2, right? Or 98.1. You're like, we're okay. It's okay, right? Hey, now our favorite part. What's our favorite part? There's a lot of writing on his board. I know this is Autumn's favorite part.
Calculator.
It's where we say, man, that's a lot of stuff. I've got a conclusion up here. I've got to set up the hypothesis test. I do my interpretation. That's not going to be hard. It's where I might mess that up, right? Or I might forget this TCDF thing, right? No worries. Where is the really cool button? That's what we want. We all want the what?
Technology.
The really cool stat button. Let's go find it. And everyone, when we do this, you're going to see how much we don't have to do, Autumn. You're going to like this. And Gary, I'm telling you, you're going to like this. Now, did anybody need a cell phone snap this? At least we got it on video, right? Are you sure? So we'll be on video. Watch what I erase. You ready? Oh, a lot. See all this? Watch it. Calculator's going to do that for me. That cool? So I'll just put a blank.
Look, if we do the extra stuff, can we get extra credit?
It's good to show work, isn't it? Calculator's going to do this for me. Right here. I want to put that. It's going to do all that for me. So let me take this out. It's going to do that for me. It's going to do this for me. Isn't this cool?
Can you give me a solution?
There's only hey, there's only one thing. And when I left it with this yellow chalk. That's the only thing the calculator's not going to do. Will you remember that? Sometimes you're sitting there going, how did I get this T crit? I should put a box on it. It's the only thing the calculator's not going to do.
Yeah, that's new.
On the table. Or if you use that inverse T bar. It's the only thing you're going to have to get from what? This. It's the only thing. I'm telling you. So you'll pull it out and you go, let me get my critical T value. It's based off the what? This came from what? That little level of significance which Gary is always given. But after that, you'll be nice and good to go because all you do is let the technology do the work. What's most important to us is that we can interpret things and understand what it means. If our P value is really low, what are we going to do? Reject the hoe, right? We'll have evidence. We'll have evidence for it. All right, you ready to go to the cool button? This is the fun part. And when I say highly encourage, I highly encourage you to use this button. Couldn't have I messed up that mathematics there? You bet I easily could have messed up like a parentheses or something. This is going to keep us safe. So clear this out. Go to stat. Go to tests. We're not looking for confidence symbols anymore. We're looking for a test. What kind of test? Well, what letter is that?
T-test.
We're looking for T-test. It should come up soon. Tia, we're looking for Tia. Oh, for Tia. Everyone, Tia. Tia. We're looking for T-test. Tia, where's T-test?
Number 2.
For Tia, there it is. T-test. There it is. We're just going to remember it because of Tia. Thanks. All right. And I think this is going to be straightforward. Now, data is if you went out, Gary went out and did a study with some of his colleagues and friends, and they did something, but we're just getting the stats out of the book, right?
Right.
We won't put that yellow number, it's okay. But we'll put all this somewhere. Let's go through it. All right.
Come on, dude.
What's this first one? What's this mu thing?
98 point.
98.6.
That's the status quo. That's given in the first sentence all the time, isn't it? You'll find that in the first sentence. What was the status quo? 98.6. All right? Now what's X bar?
98.2.
98.2. You're rolling? What's this SX? All this is given in the problem. What was the sample size? We don't have to hit the degrees of freedom because the calculator will do it for us, right? Even though we could. Which one of these three tests is it? Is it a left-tailed test? Is it a right-tailed test? Or is it what they call a two-tailed test?
I don't know.
Left.
Which one is it? It's all based on what we saw earlier, right? So which one is it? We're looking there. It's a left-tailed test, right? Remember why we shaded on the left and all that? So when I'm going to go to this one, how do I make it highlight there? You go, wait, you got the wrong one. Okay, wait, I got to get to this one, right? I mean, Brittany, it's so important I hit this. This is very, very important, right on? I got to hit the right one. It was based off this. Remember the research started was lower than? All right. Boom, it locks. And when there's a calculate and draw, I don't like draw. They draw a bell, it's not nearly as pretty as ours. Trust me. I don't think it's nice as ours. I just do calculate. Seriously, I would tell you if I like draw, I don't like it. Our drawing's way better. Way better. We got the color code, right? Yellow and white. All right? just like we thought. Everyone, please make a note, this is called, that's the p-value.
Wait a minute.
How cool is that? It gives us the p-value, what else does it give us? It gives you what? That t, the sample test statistic, it gives everything we want. This is awesome. Garrett.
So with this, it gives us both of the approaches.
You bet. The most important numbers. Gary, it gives us the most important numbers. What was this? I go there and what is it? And then we plot it. And if it falls in your critical region, Sierra, we're going to reject the null hypothesis, right? And then it gives us the p-value. What was the p-value?
Zero.
So I do want to point out on that p is the p-value. Ooh, question.
So we're still going to be required to write, you want all 5?
Key portion is this? Yeah, I do want to point that out. So I'll hit this so everyone hears this. And it's important when we do a hypothesis test, it does involve writing, but we get this class, we get the next class, Tuesday, and then we get Thursday again to do this stuff, and you'll be well experienced. I know the first time it's kind of like what? You know, like when everyone said it was kind of like, whoa. Use it again, you'll be very good with this. So we'll always start out with the setup, then the requirements. We'll perform the classical approach. If you want, right after you perform the classical approach, you can state your conclusion because you'll know it. But we will also perform the p-value approach. Now later on, maybe I'll get to the point where I heard what some of you are saying. You're like, you know, after you've done it a couple times, there might be another problem where, like, on a test, I might go, okay, and this time, I don't need you to show me both approaches, right? Hey, so, but it is important we do all those portions. And we're going to state the conclusion, and we'll interpret the p-value. Hey, one last thing. What if your p-value is low? What do you do? Reject the O. Good. So, can't you just hit that button every time and look at the p-value? And if it's lower than this, you know the whole story? Do you follow me? You know the whole, you know the solution right away. That's what's important. So you can always look at that p-value and go, oh, is it higher or lower than this? It's going to tell me what I'm doing. If it's lower than this, we reject this. If it's higher, there's not evidence, right? Does that make sense? And do things in this world happen with like 13%, 20%? Yeah, so when things like that happen, we say the results are not statistically significant.
Can you repeat?
Yeah. Yep. Shh. Everyone, just real quick. There's one last thing I want to say. Real quick. In this world, do we get things that happen with like 25% chance? Absolutely. Like things that happen. There's a 25% chance that things happen. So if we got a p-value of 25%, it's higher than this, then we're just going, okay, those results are not statistically significant. You follow me? It's when that p-value is what? Some extremely low probability, and we're like, you must be messed up. Cool? Hey everyone, have a great weekend. Super job.